study. The ACS study guide is going to be the most important thing to go through and study. Okay, the people that wrote the ACS exam also wrote the study guide, so use that to help out. At this point, you're looking at a lot of shipping costs to get it mailed to you or purchased, so it probably makes sense to either use mine in any of the tutoring office hours or go to the library tutor center, and they've got at least one copy of it as well. Okay? So use that information to get that practice so that you're ready to go. After that, you should go to old exams. So review all of that old material and make sure that you know why you got things wrong. You know how to prevent getting it wrong when it comes to the ACS test. After that, Sapling practice. In theory, well, it's not in theory, it's actually true. There's a lot of practice available on Sapling. Okay? Once you've completed the homework, all you should be doing is writing out answers on using pen, pencil, and paper, and then just clicking submit answer until you get the answer or get Sapling to spit out the answer. You can then compare what you wrote on paper to what Sapling is telling you the answer is. Okay? Do not sit there and play the frustration game of drawing things into Sapling. Okay? For practice, just get to the answer as quickly as you can to compare what yours is.
So practice, do you grade for the practice?
I do not grade for practice. Okay? If you're concerned about that at all, feel free to talk to me after class and I can show you exactly how I will go through and assign the Sapling grades. It is long and tedious. The last thing I would do is go to the textbook. The textbook does have helpful homework problems. You don't necessarily have answers available though, and you won't be in that same kind of multiple choice format, okay, which is what you'll see on the ACS test. So if you've really done that much practice that you can jump to the textbook, you're probably fine. Okay? I do want to mention the Sapling homework. It is officially due May 4th. There seems to be some confusion about my 30% leniency on this. We only need to achieve a score of 30% to get full credit for the homework, okay, for the last 4 or 5 assignments. If you get a 30% score, you no longer have to do that homework. You now have 100% of the points. So continuing to enter things into Sapling is a waste of time. Okay? Where do you find that score? I took a screenshot. You can see I did very well. Okay? As from the student view, and you can see each of the lecture assignments with the homeworks, and it spits out a score. Okay? Very clearly, 0 out of 100 is not going to get you any points. Up here, I've got a score of 36.9 out of 100. Okay? I don't have to answer any more questions within that assignment. It'll be a 36.9. If I do choose to look at those other questions, I can click Show Me the Answer. It will not change this score. Okay? Because Sapling is currently looking at that as an unanswered question. So you've already got it wrong. Clicking Show Me the Answer doesn't make it any more wrong. Okay? Clear that 30% number, you've got full credit. Okay? Show me the answer for everything else. If you're under that, you'll then fall under different categories, and that was that grade system that we talked about a while ago. Okay? So please, I really don't want to see scores higher than 30% on those last few assignments, because what that means to me is that you're wasting your time. You're not spending it appropriately. Okay? Questions about that? Any last panic questions before we actually look at review stuff? Okay. I have really high hopes. I think you guys can do very well. Okay. So Fischer projections are ultimately just another way to look at an individual molecule. So when we first started off organic chemistry, we looked at Lewis structures. Then we looked at the Vesper model. Then we looked at line angle drawings. Then we looked at the organic simplifications, assuming hydrogens, implying hydrogens, assuming every point's a carbon. All of those fun extra rules we just kind of stacked on top and slowly started adjusting accordingly. When we got into chiral structures, we had to then go back towards our wedges and dashes using our line angle structures. And we needed that to help us represent the difference between our structures, particularly when we reflected through a mirror image. All right? Uh-oh. I didn't think that one was showing up. We also looked at that classifying a pair of molecules. Yes, you will have to go through and deal with this. So it's going to be a good thing to get that flow chart kind of settled down and figured out. All right? And it's actually within this that Fischer kind of adjusted his new viewpoint on structures and how to go through and draw them. Because if we look at a very complicated structure that has a whole bunch of chiral atoms, it can be difficult to compare that to another structure, decide are they enantiomers or diastereomers or some other configuration. So what he tried to do was come up with a new notation that standardized how you would look at structures. And as long as you always converted your structures into that standard notation, you could then very quickly and easily see the relationship between those individual structures. All right? So, Fischer projections. It's just a structural representation that's slightly different from our line angle format. Shoot, I left the model kit in my office. So if we've taken this structure that we've got in our line angle format and we want to change that into our Fischer projection. So Fischer went through and said that he wants to reorient the molecule. He's going to find the longest carbon chain. So in this case, we're going to be highlighting through here, that longest carbon chain, and we're going to orient that on the vertical axis, so straight up and down. Okay? When it's straight up and down, though, we have two possible ways we could orient it. We could have our carbonyl carbon. This star could be our top, or why not? Circle could be the top. So we said, okay, we have to come up with a new rule to make sure that when we're looking at our structure, it is always in this correct format. Okay? In this case, he said you always got to put the stars up top. Okay? So which atoms are your stars? Okay? Supposed to be kind of funny. Our star is our highest priority carbon. So we would go through and take a look at the carbons at either end and say which of those carbons has the highest priority. Well, how do we determine priority? What's attached to it? The atomic mass of the atoms attached. Take a look at our star carbon. It's attached to an oxygen. Take a look at our circle carbon. Carbon or hydrogens out the other direction. Our star carbon is our highest priority. So we're going to now draw our structure such that our star carbon is at the top. And I'm very, very sloppily going to attempt to draw this. There's our star carbon. And we've got our circle carbon down at the very bottom. Okay. And now what we'll go through and do is just link our carbons all the way through the middle of this. How many carbons do we have there? 1, 2, 5. So I just need 3 more, right? Did I do that math right? 2, 3, 4, 5.
6, right?
5 carbons in the chain. We'll focus on that in that chain. Okay, so we now have kind of our basic skeleton organized. The next part of this is that when we take this structure, we're going to rotate those sigma bonds. Okay, any sigma bond that's within that carbon chain, and we're going to rotate them in such a way that if we were to look at our Fischer projection or pick our star carbon, if we start at the top, that anything underneath it and above it must be aimed away. So we're saying that that's now a dash to the next carbon. Okay. Now we change our viewpoint and move to the second carbon. Okay. And within this viewpoint, we again have to assume that anything above it and below it is aimed away from it. So we already have the dash there, so we'll draw in our dash on the next one. Okay. And we rotate to the third carbon. And now when we're looking at that third carbon as a viewpoint, we do the exact same thing. We have to be looking that our carbon chain is aimed away from us in both cases. So we end up with dashes all the way down our backbone. Okay.
Is this always like this?
It is always like this. Yes. Okay. If it's not like this, it's not a Fischer projection. We can't use any of the abbreviation rules that Fischer comes up with. Yes.
Can you explain why it's dashed? Like I thought if it was, I would assume this is why it shouldn't be the opposite. But you're not going to.
So Fischer went through and picked each carbon atom as a central point. So we start with our star carbon. We pick that as a central point, and we want to look at that carbon and the things arranged around it, such that everything that goes directly above it is aimed away from it. Everything that is directly below that carbon is also aimed away from it. Okay, away from our viewpoint. Okay, this would be really helpful if I had thought to bring a model kit. Oh, cool, thank you. So, if we're going to pick, actually let's keep that connected. If we're going to pick this central carbon, okay, as our standard viewpoint on where we're going to center everything from, what we're going to do is we'll assume the blue atom up here is a carbon and this knot in back is a carbon, right? So what we're going to do is change our viewpoint. We're going to take that center carbon and we're now going to turn the structure such that our blue atom and our other carbon are aimed away. Okay? That is Fischer's view. It says with that as my center atom, the blue atom and the black atom are both aimed away. The red being the center.
Two facing that way.
Yes, exactly right.
So the blue carbon on top would be facing away, but
It's facing away.
wouldn't the bond between the red and the black remain? Would that become dashed then?
It's also going to be dashed. So both our knot and our blue are dashed,
Okay.
and our knot and our black are dashed. With our first carbon on that list, our star, we didn't have anything above it, so there's nothing to look dashed at up there.
Then why aren't there wedges and dashes on the show?
We haven't gotten to it yet, but you're right, there are wedges and dashes in here. If we're now again going to take a look at this carbon, what about the other two groups attached to that sp3 carbon? Where are they now located?
They're closer to us now.
They're going towards you. So in that viewpoint, every single one of these carbons is going to have two bonds going away and two bonds going towards you. So we would go through, and this is, I think somebody artfully called it the bow tie. Okay, so we now have these bow ties coming out towards you. And what Fischer then went through and did was with that exact model. Okay, if we went through and did this guy, we looked at where the green one is. Where's the green one located, left or right?
Our left, your left.
Stick with your left.
Left.
So it's on your left. So what he would do is then draw the green atom on the left-hand side, which is left. This is left, right?
I think so.
Good. That's our green atom. Where's the red atom?
You're right.
On the right-hand. What did I just say? I said red.
Yeah.
We'd put the red atom on the other side. Okay? We've done one carbon of this structure for the Fischer projection. Only one. So what has to happen? Now Fischer goes through and says, well, I need to move to the next carbon atom. Next carbon atom is now the black knot. Just as we did before, we need to orient the molecule so that every atom above it and every atom below it are aimed away. So we change our frame of reference every single time we move to a new carbon. Yes, oh my God is a very valid representation for this. Okay? And now that we're at that new carbon, you'll notice that, again, we want to orient it so that our groups, the other two atoms, are now naturally pointing towards you. And we could again go through and label where those atoms were. Yes?
So regardless, it's always going to be dashed.
The up and down will always be dashed.
Right.
Anything in that vertical
Vertical.
axis is dashed.
For sure.
Anything in the horizontal axis
Can vary. No.
will
Towards us.
always be wedged.
Oh, okay.
It has to be for the Fischer projection to hold true.
What does the G represent?
That was the model that I'm holding in my hands,
Oh.
which anybody watching this video is going to love,
Gotcha.
because they can't see it.
So where is another bond? Carbon has
Take a
four
screenshot.
bonds.
What's that?
Each carbon has four bonds, right?
Carbon, each carbon atom has four
Two
bonds, and we're
dashes.
looking at our,
Oh,
we'll
one,
end up with two dashes and two wedges.
Where is the other dash?
So when we go through, let's pick a carbon atom. I'm going to go ahead and call it purple right in the middle. Our carbon atom has four things attached to it. There's one dash bond above it, one dash bond below it, one wedge to the right, that is right, one wedge to the left. 4 things are attached. Why is this method already, to me, ugly? We've brought in a bunch of wedges and dashes, whereas before I at least had 2 solid lines. I only had to deal with 1 wedge and 1 dash. Okay? So absolutely, with this structure, this method is getting really, really ugly. Okay? The whole point of this Fischer projection, though, is to change our orientation so we can very quickly determine R and S, or officially actually D and L, off of the structure. Because every Fischer projection has dashed bonds in the vertical axis, and every Fischer projection has our wedged bonds in our horizontal axis, we can come up with a simplification. Instead of showing them as dashes and wedges, what can we show them? Just a normal solid line. And as long as we know we are in the Fischer projection and that every solid line within that vertical axis is a dash, and every solid line in our horizontal axis is a wedge, we can come to and draw a whole bunch of quick conclusions about our structure. Okay? So what we could look at would be this setup. Okay? I tried really hard to make sure this was an accurate representation and these structures matched, but I can't guarantee it because I really don't like the Fischer projection. Okay? How do you come up with that orientation? Okay, one possibility is you rotate our line angle structure in your head, 3 dimensions, to get it set up to draw those projections on the right. Okay, I can tell you I did not do that. Okay, I went through, built the model kit, did all the rotations to get this structure drawn out. Okay, why did Fischer go through and do this? Well, we can now take a look at a stereocenter. Within this structure, that red carbon is a stereocenter. And what he ended up noticing is our higher priority group is on the right-hand side, gets labeled as a D. Okay? It also comes out as an R enantiomer, or an R stereocenter. So we have now a right and left association with it. Kind of cool. Okay? Sort of. Okay? For all of you shaking your head, I do agree. I don't particularly like it either. Yes?
Why is that carbonyl bond in the same plane as the paper?
What's the hybridization of that carbon? sp2. Where are all those bonds? They're all on the plane. Both the leading carbon and the tail carbon we usually ignore because they aren't stereocenters. So usually when we're looking at the Fischer projection, we're drawing it up so that we can see the stereocenters in this kind of bow tie sort of format, which means that this version of our Fischer projection was useless. It's not even that it's invalid. It's just, why do we care? It's not a stereocenter. We have 2 atoms that are identical within that. There is no need to look at that in a Fischer projection. Okay? So all that's happening with the Fischer projection is changing the orientation of the molecule so that we can look at it in an easier, potentially easier format.
That's R, you said?
I don't remember. Did I say that wrong?
I don't know.
Yeah, you said it.
1, 2, 3. It's counterclockwise, but remember, our lowest priority is actually this CH3, which is located where? Towards you, so we're looking at it backwards. So it's R. They are both wedged.
How does that even work? Like I was gonna say, like, are they not repelling? I can't think of the word.
There is no repulsion. This officially, oh, okay. Officially, what's the bond angle in each of these cases? It's still 109.5. What we've just done is changed our viewpoint of it, and if you look at a tetrahedral carbon, right, and you kind of go cross-eyed at it, right, and you ignore or look at it with one eye, cover one eye, get rid of that 3-dimensional aspect to it, what do you have? You have one line up, one line down, one line to the side, one line to the other side. You have the exact shape that Fischer is drawing out here. The part that's really hard for us is that we have the ability to pick out 3 dimensions, and we can tell that these 2 side ones are coming out at you and the 2 back ones are going away. Right? But officially, it is the exact same drawing. Right?
So
And
there's
there
no
is still no repulsion. So you have to remember what Fischer is drawing is a three-dimensional representation of this model. There is, the repulsion here is the same there as it is if I turn it to the side,
Oh, very true.
as it is if I turn it over. Okay, it's the exact same repulsion. Okay, so why on earth would we bother to go through and deal with this? No, I get to blame people. We get to do it because of this structure. What is this structure? Beyond stupid.
Super alcohol.
Super alcohol.
Sugar.
It's glucose. Okay. Talk to any biochemist, talk to any biologist. How many of them like this viewpoint of this structure? They probably hate it. What the heck does that wedge mean? What's that dash? Why are there all those sharp pointy lines? Okay. So what Fischer went through and did was took this weird orientation of the molecule, redrew it, so that instead of focusing on all these wedges and dashes, when we look at sugar or glucose, all anybody sees in biochemistry is that. What does that structure necessarily imply? All of the stereochemistry that is implied in our line angle format. But it's now been put into a position that is easier to digest. Okay? That is really why Fischer was helpful, is it was looking at biological molecules and in fact all of these sugars. Okay, so why did he invent this whole new system to look at just freaking glucose? That's only one sugar. Why should we worry about it?
It's responsible for a lot of stuff.
There's an entire family tree of sugars. What we've got here is adding a single carbon on and looking at it acting as a sugar molecule. This family tree is just for the aldose family. Guess what else we have as far as sugars?
Ketose.
We also have the ketoses. Right? So all of these structures all imply stereochemistry without having to use the wedges and dashes because they have been organized into a format that shows or follows Fischer's rules. And with those rules, we can draw some conclusions very quickly without having to evaluate, assigning R and S and all of those extra things. So the reason Fischer becomes helpful is really for biochemistry. For organic chemistry, where typically we avoid chiral molecules like the plague because they're a pain to deal with and it makes it difficult to isolate or separate or any of those things, biochemists can't get away from it. So they developed a system that tried to make that confusing subject of chirality at least easier for them to understand within their limited world. Well, that didn't come out very nicely. Okay. It's a pretty massive limited world, so I mean, it's like saying Earth is our limited world when we have the universe to go out into, but Earth is still really big, right? Okay. So it is a nice simplification in that we can draw these conclusions. When you move into biochemistry, turns out actually this is only half of the aldose family. Anybody know what type of aldose sugars these are? What type of aldose sugars are these? They are all the D sugars. Why are they the D sugars? Because if we go through and take a look at the second to last carbon, the OH on the second to last carbon is on which side? The right side of the structure, also known as our dextro side. They're D sugars. What would the opposite be? L sugars for levorotatory or being on the left side. So if I wanted to make any one of these an L sugar, what do I need to do? I go to that second to last carbon and I put the OH on the other side. I now have an L sugar. Very quickly, I just changed drastically the chemistry of that molecule without having to deal with R's and S's and all that fun stuff.
So the ketose thing?
Okay. Ketoses will go through and do the same thing. We'll have both L and D ketoses as well.
So there's D on L for just aldose itself.
For aldoses and ketoses. All that this family tree shows here is for the D aldoses. There's another mirror image of this, or not mirror image, mirror image of that second to last carbon that is our L aldoses. Then we have the D ketoses and the L ketoses. All of those families are organized because Fischer was able to see or organize that information in such a way that it was quicker and easier to evaluate than looking at all of the stereocenters in an individual sugar molecule like we had drawn up in that line angle format.
So when this Fisher Price guy was doing this, didn't he start with biochem? Or
Well, he did, but what's the prerequisite for biochemistry? Organic chemistry, because what we're trying to teach you in organic chemistry is the fundamentals of how those biological molecules interact to get you biochemistry. Alright. So Fischer is something I'm not a big fan of, but it becomes a lot more important when you move into biochemistry, when you start to look at these sugar molecules and you have to deal with their nomenclature system. Good luck.
Thanks.
You're welcome. I had to teach it this semester. So if I have to teach it again, it'll be good luck then too. Yes?
Can you go to the previous slide, please?
This previous slide?
Yeah.
Or here?
No, previous. Before this. With this one. I don't understand why we have here, we have the line angle format, we have 5 carbons, right? 6
Yes.
carbons. How come here we only have 5?
1, 2, 3, 4, 5, 6.
Oh, okay.
It is there.
And why the last one, we don't have the dash or ratios?
Why did I not put it on the last one?
You know,
Because it's not a chiral center. Shouldn't have actually put it on this one either.
Yeah.
We don't have to specify that with our dashes and wedges because it's not a chiral center. Here I didn't include the dashes and wedges because it's not a chiral center. If we go through and look at the sugar molecules, did we specify dashes and wedges on that last carbon? No, why not? It's not a chiral center.
So we only
Okay.
specify.
Fischer is really only useful for the chiral atoms. We don't really care about any other atom because the orientation doesn't matter. We wouldn't care about it over here either. You'll notice that last carbon, do I have a wedge and dash? No, because it's not a chiral atom. Does that make sense? So, within your Fischer projections, it can help you sometimes look at the relationships between individual structures. Let's see if I can actually see one on this. Eyes. What is the relationship between... Oh, this doesn't quite exactly work. Here. Let's just cheat. That's what I'm doing. What is the relationship between these two structures? They're mirror images. They're enantiomers. We can see that very quickly. If we drew this out in the line angle format, all those sigma bonds flip, rotate, spin on top of each other's head. You'd have to go through and flip, rotate, spin every single one of those to get them into the proper format where you could see that they were mirror images of each other. Okay. With the Fischer projection, because he's gone through and said, no, you cannot rotate that. It must be this way. We don't have to worry about all those possible manipulations. So the Fischer projection can make it easier to see the relationship between structures, be it enantiomers or diastereomers. If I didn't do that erasure, or sorry, that change out, now what's the relationship between those two? Now they're diastereomers, because one position stayed the same. Okay?
When we're looking at the difference between an enantiomer and diastereomer, can we use that if one position stays the same, so we don't have to use
Yes.
diastereomer?
Yes.
Do we have to study Fischer?
Fischer projection, you are responsible for being able to interpret. That's why we talked about it again.
Okay, for the final?
Yes.
What is it, when we're doing the Fischer projection, how do we know which side is like the, or like the glucose, where it's like the OH is on one side and the H is on the other?
Uh-huh.
Like which, or how do we know which side it's supposed to be on exactly?
So there's two answers for that. Biochem answer. We call it glucose, so that's the way it looks. Sorry, but that is kind of how it works. The official answer is we take a look at our line angle format and we follow the rules that Fischer put together.
Yeah.
We set it up so that we reorient the molecules so that our highest priority carbon is on top, lowest priority carbon is on the bottom. And then we go through and we have to rotate each and every one of those sigma bonds to make sure that those atoms are wedged coming at you. When you go through and do that, that line angle directly converts across into the Fischer. So you have to go through all those silly rules. Right. This is one of the reasons why that's very rarely done, and most biochemists just stick with the Fischer projection. All right. Not bad, right?
I think this might be the first question, but for like the OH groups, right? There's just a hydrogen, so like other than that, never mind.
Okay. Oh, you got one? Yeah?
Oh, never mind. Sorry.
It's contagious. So we've got our aldoses. I'm not sure this is going to be as big of a deal, but we're going to throw it in here too. Biologists, familiar? When we look at sugar molecules, are they represented typically as a straight linear structure? No, they fold back on each other and form these rings. The chemistry behind that ring, second semester OChem, right towards the very tail end. Okay? So you look at the mechanism for how this reaction works. Or you do it in biochem and they just tell you it does this and you just have to know it. Okay? So that can make your Fischer projection even more confusing because we now have a ring structure. Well, Fischer is trying to show it as a straight line. So if we look at our Fischer projections for the rings, that gets very weird. We just kind of have this wicked long bond through an oxygen. And that bend right there, what does that bend signify or that point signify? There or there or there? Absolutely nothing. It's just the continuation of the bond.
That was a loaded question.
Yeah, it was, I know. Okay. It's just the continuation of that oxygen bond all the way around. Those are not carbon atoms. Okay. So we could look at it in the Fischer projection, but yet another guy came along and said, Fischer, your structures look awful, I can't interpret that. So he went through and drew out the Haworth projections. Guess what his name was? Haworth. So what we did was just took that ring, and we now visualized it from the side, and you can now see the orientation of each of those individual groups. We've already kind of looked at Haworth projections already. When we looked at general ring structures, we had cis and trans. And we used wedges and dashes. We could just as easily have shown an up bond versus a down bond. Okay, and that's really our official Haworth projection. All right. Yeah, so I'm not sure how much more you guys really want to look at that. Probably not a whole lot more. Anybody have any questions about that? Okay, regretting Fischer.
I have to do all this?
What you're responsible for is being able to look at those images and draw some conclusions about it. Okay. And those conclusions, particularly when it comes to Fischer and Haworth, are really looking at determining the relationship between two structures. Are they enantiomers? Are they diastereomers? Okay. Are they stereoisomers? I don't know, come up with some other different name. Cis and trans isomers or isomers. Okay. So it's being able to identify all of that extra stuff. These slides officially came from the biochemistry class that I taught this semester. Okay, so you aren't really pushing too much into this. Well, this slide, and this slide are all from biochem. Okay. So the rest of this is just practice. So if you guys have questions, I'd much rather target the places where that you feel you have some kind of weakness. If there aren't particular questions about that, what we'll go through and do is look at just some practice problems. So if you watch the lecture that I posted on Friday, I left these two images up on the slideshow for all of a second, 2 seconds, because officially each class is 75 minutes and I didn't want to overshoot new material. Okay? So, you guys want to work on these practice problems, or these practice problems? Take your pick.
First one.
Want to do the first set where we got all of them? Okay, so we'll work with a couple of these. I will start with that first row. just to get you some practice, get you an idea on what's happening with these. All of these reagents do what? These are all quick sedations. Try that again. Oxidations. Okay, all those are oxidation reagents. So what we're looking at doing is adding oxygen to our structure, okay, in a variety of different fashions. Okay? These are actually shown in reversed chronological order. So, ozone. What does ozone do? Doesn't like having 3 oxygens, so it is very, very reactive. So what that oxygen will do is it will react with your pi bond. Let's say these are carbons of our pi bond, and the oxygen will insert itself in such a way that we end up with this 5-membered ring. Where was the pi bond? It was initially connecting those 2 carbons. It is no longer present after ozone reacts. So this is our highly reactive intermediate. Okay, this intermediate can now get put under various conditions, and this is where it gets a bit odd. In that first column with DMS, we refer to that as ozone under reductive conditions. It's kind of odd. Why is that odd? What does ozone do? It oxidizes. Why are we saying reductive conditions? Ozone is so reactive that it can go through a secondary oxidation reaction. So we could oxidize this molecule a lot or just a little bit. If it's just a little bit oxidized, we're looking at reductive oxidation. If we're looking at really oxidized, we're looking at oxidative oxidation, right? For lack of a better description. So the result when we go under reductive conditions is what we'll do is take our ring, and what I'm going to suggest you do just to kind of get an idea of this, all right, is we're going to stretch that double bond, really, really stretch it out. Right next to the happy little tree. 1, 2, 3, 4. Do I have 6 carbons in that?
No.
Yeah.
It's Monday.
There you go.
There's our 6 carbons. Did you say a coffin? That's not very... Well, let's fix that. We're going to stretch the double bond when we see ozone, and what we're going to do is stretch it so much that we're going to break it open. Okay, so we're going to erase the middle of that. And what kind of reaction was this? Oxidation, which means we add oxygen bonds. Put an oxygen on both ends of that. Okay. Under reductive conditions, this is where we end. All we've done is stretch that double bond, dropped in our 2 oxygens, and all is good. What happened to the 3rd oxygen? It reacts with the DMS to make DMSO for that last oxygen. Okay, so that's a byproduct of this reaction. If we don't have a place to dump that extra oxygen, we're running under our oxidative conditions. Okay? Depending on potentially typos, it may be H2O2, which is a secondary oxidizing agent, or it might run okay on its own if we just add water. Okay? Ozone may be strong enough to completely oxidize. And what I mean by that is that we're going to go through the exact same process that we just went through. Okay, so we've got our super stretched double bond, where I will probably miscount carbons again. So 1, 2, 3, 4, 5, 6. Now I probably have 7. 1, 2, 3, 4, 5. No, I got it. There's our 6 carbons. We'll go through the same stretching. We'll erase our double bond and put in our oxygens. But now we have to run under oxidative conditions. Well, for oxidation to occur, we have to increase the number of oxygen bonds by, at the same time, doing what? Reducing the amount of hydrogen bonds. Reducing the amount of hydrogen bonds where? Around our reactive carbon. Our reactive carbons were where our double bond was. So we want to look at those reactive carbons. What else is attached to those reactive carbons? Hydrogens. Do we have hydrogens on that reactive carbon? Yes. We need to oxidize. So we remove those oxygen or those hydrogens and replace them with an oxygen. How many bonds does oxygen need to have? 2. So what's that second bond? We'll just add a hydrogen to kind of fill the gap.
Wait a minute, there's 4,
The 5 oxygen.
So yeah, it may not actually come out as balanced. Yes. So with this reaction, what's the mechanism? Good question. Check it out online. I didn't even bother to look for it. You're not responsible for the mechanism. What you're responsible for is the product. Okay? So in this case, what we end up doing to our alkene under oxidative conditions is we will split the alkene, turn them into carbonyls, and look for reductive hydrogens. If we have a reductive hydrogen, we must remove it and replace it with an oxygen bond. Yes?
So our product is no longer a ring?
Our product is no longer a ring. Exactly right. How would this likely get written out on the ACS test? Son of a freaking heck. And then they would probably show a bunch of rings. Everybody would go, well, it's got to be one of the rings because you can't break open a structure.
No.
Okay? So when you look at ozone, it will break that double bond. If we started with a ring, we end up with now a straight chain structure. What if it wasn't a ring?
Straight.
It's still going to be straight. The double bond will disappear still.
Right.
But now those 2 carbon chains aren't connected to each other,
No.
which means we have 2 pieces. Okay?
That's every time dealing with ozone?
Every time dealing with ozone. Okay? What happens with our permanganate?
hot, do you use temperature?
Yes. Permanganate under hot conditions will do the same thing.
Oh wait, it breaks, so it's on a ring also?
We're still running it with starting with a ring, yeah.
It just makes carboxylic acid on it, on the ends.
Yep. So it'll do the exact same thing as our ozone dome. It splits that alkene, drops in the carboxylic acids. What if it was under cold conditions?
Do it slowly.
Pretty close. It would do the same thing if it was under cold conditions as our OSO4 would do. Both of them result in the same situation, which is we take our ring structure, and we take our double bond, and we replace the double bond with oxygens, OHs.
Same side.
And they must be added on the same side. Because there's a top and bottom, we also end up with the enantiomer. Okay, or potentially diastereomer, depending on what our structure is. With this compound, that was dumb, it's a meso compound. So it doesn't matter what you show. Everybody see what I said there? Not the part about me being dumb, but that's a meso compound. Meso means we have an internal mirror plane. So there's 2 chiral atoms and we have that internal mirror plane. That internal mirror plane means that if I drew out the other possibility where it attacked from the bottom, what's the relationship between those 2 structures? They're identical with 2 chiral centers, which means we end up with a meso product, only one product in this case, a race. Okay. You guys want to try the next set on your own? That's some optimism there. I like the shaking of the head.
Do you mind the photo underneath the house
Oh, good question. The osmonium tetroxide usually involves two steps. You react the alkene with the osmonium tetroxide, and then you react it with some reducing agent. Okay? That reducing agent changes depending on the whim of whoever wrote the question. I've seen like 3 or 4 different reducing agents get thrown in there. So if you see OSO4, this is what you get. Doesn't matter what the other reagent is. Okay, you'll end up with this, and if they give you more steps after it, then this reacts and continues on with something else. But OSO4 with 2 steps will get you to the cis diol.
So it doesn't matter what order.
It doesn't matter what the next step is, but yeah, you're right. There will be 2 things there. 1 followed by 2, some reducing agent. All right. So go ahead and take a stab at the next one. And if you got questions, raise your hand and I'll... Okay, answers on that second row. If we go under reductive conditions, we're going to do the same thing we did before, stretch that alkene out, erase the middle of it, and drop in 2 oxygens. What we'll end up with is cyclohexanone, so our cyclohexane with a carbonyl attached to it. And then we'll also end up with a carbon doubly bound to an oxygen. Okay, what is not currently being shown to that carbon? 2 hydrogens. We're under reductive conditions, so those hydrogens stay. When we go to oxidative conditions, we're going to do the exact same result, except now with those reductive or reducible, oxidizable hydrogens. I did settle on oxidizable hydrogens, just to make sure. Okay. We're going to remove those and replace them with oxygens. So we remove one at a time. And in that process, after we remove one, we've got our oxygen. We then go through to remove the other one, and we want to add another oxygen bond. Where's the closest oxygen? The one that's already attached. We don't need to bring in a 3rd oxygen. All we've got to do is increase the number of bonds to the oxygen that's already present. All right, and we end up with CO2 being removed. Permanganate, under hot conditions, will do the exact same thing.
But do we have the OH with the manganese?
The what?
The OH, the hydrogen group?
There is no hydroxyl group with the ozone under oxidative conditions.
No, the KMNO.
When we move to the KMNO4, we do the exact same thing as ozone does under oxidative conditions. So again, no OH.
So why you wanting the arrow to the second?
Everything that happens under the KMNO4 column is the exact same thing that happens under the ozone and peroxide.
So we have the OH. Oh, we don't have OH.
Is there an OH there? There is no OH. Okay, then we could take a look at our osmium tetroxide or our permanganate. We'll end up adding on our 2 alcohols in a syn addition. Interesting feature of those 2 alcohols, one of them is a stereocenter. What about the other one? Actually, that was a lie. That's not a stereocenter. I looked at it. I caught it before you made fun of me. No stereocenter because our carbons are the same all the way around. Good eyes. Right? So we don't have to worry about a stereocenter on that. What happens with our alkyne? Similar process except without those reducible hydrogens. What will end up happening is we completely cleave our structure open. Make sure I get my carbons right. Oops, I did have it right. We'll end up with the carboxylic acid. So we're going to cleave the triple bond straight through the middle and replace it with oxygen bonds. So we'll end up with our carboxylic acid. We need to account for 4 carbons. All 4 carbons are present. There's 1, there's 2, and we get 2 of those molecules because it was symmetrical. Okay. We run it under oxidative conditions. What happens?
The reactive carbons get oxidated further.
We get the same thing. There is nothing to oxidize further. We're stuck there. With our permanganate and the osmium tetroxide.
Does it cleave
Should have clicked this one a little bit closer. I don't think we see a reaction with our triple bond. Pretty sure your book doesn't show it, and I've never seen it with one, so I'm not positive on that one. But I think these are all NAs. Not applicable.
At least a lot of time, no.
Sorry. I built it quickly.
So there's no reaction.
What happens with our alkyne, our other alkyne, our terminal alkyne? We'll get our carboxylic acid and double carbonyl. Did you really just say that? You mean CO2?
Yeah, CO2.
Carbon dioxide? Okay, because it's that terminal position, we can fully oxidize that out to our carboxylic acid. All right, what happens if we change our conditions? Same thing. Okay? Fun stuff. So with your oxidations, stretch that carbonyl or your alkene, erase the middle of it, drop in your oxygens, and then see what you've got from there. Okay, be it reductive conditions or oxidative. The reductive conditions, you will probably see DMS. How else can DMS get written? Can I erase everything? DMS can also get written out as CH3, sulfur CH3. Be kind of aware of some of the other things that you might see. Okay? So that is DMS. Dimethyl sulfide. More fun practice. Unless you got questions, you're going to keep getting me throwing reactions at you. So I'll give you, look at this one. Say that I've got 2 bromines. It's a good way to get 2 bromines on a structure such that they are trans of each other. We can do an addition reaction where we add Br2, there's our 2 bromines, to pi bond. Yeah?
Yep.
Okay. What's the reactive part of my alcohol? Okay, we got a couple things. We have the OH, as in we could look at that hydrogen being acidic, or we also have what I would reference as the CO. So we got acid-base chemistry, and then I have in blue either substitution or elimination. Why do you want to do elimination? We need a pi bond, right? So let's see if we can push that elimination reaction. What do we need to do the elimination?
Heat.
Heat?
And the
Sorry,
base.
Janine. We do need a strong base as a possibility to run an E2 elimination. What does that butoxide react with? Hydrogen. Which hydrogen?
Hydrogen attached to tertiary.
The most positive hydrogen, which is the hydrogen attached to the oxygen. You wanted it to react with the hydrogen on the ring to get an elimination. So T-butoxide is going to be a bit of a problem here. Okay. Let's say, for instance, let's somehow just say we got a base. We throw that base in there, and let's magically say that somehow we get this to work. Takes that hydrogen. What happens to those electrons? Whoops, that's an eraser. Move the electrons in to make a pi bond, and we kick that guy out, right? What is that guy? Is that a good leaving group? No. So is a base going to be a good option for this? No. What we're going to have to do is convert that OH into a good leaving group first. To make it a good leaving group, what does it need to be? We could protonate it. To protonate it, what do we need to add? an acid, we could run into an issue now of what acid do we add.
HCl or HBr.
Just to be obnoxious. Which of these three, and we'll end with this, by the way.
It's just a-
H2SO4.
Answer, H2SO4. Why?
Why?
Well, can't use hydrogen for it.
Nope. HCl is going to produce, what is that?
Yeah.
Cl minus, which is
Oh, another.
a nucleophile, which will compete with the mechanism. So the acid that we choose must be a non-nucleophilic acid. H2SO4 is one of the only ones that we know of. The other one, which I doubt you'd see, but just in case, so we could use H2SO4 or interchangeably, you guys remember from my troubles from lab, you can use phosphoric acid. Okay. Both of those are non-nucleophilic acids. They'll give up a hydrogen to our OH minus, so we run that acid-base reaction actually first to make a wicked good leaving group that can leave. The hydrogen can then be removed using the heat. That gets us to our alkene. We can then react the alkene with bromine. As Lulu was suggesting, we could also have gone through a substitution reaction, which would not have been quite as nice, but we could have done that. We could have said reacted it with maybe HCl, and that we would have gone through and done our substitution, where we now have a good leaving group that we don't have to worry about the reactivity of that OH. And now we could go through and react that with a strong base like our T-butoxide to go through and get our alkene. Both of those methods would work depending on your instructor. Me, personally, I don't really care as long as you're proving that you understand the chemistry. If you take it with somebody else, the method that Lulu suggested, as nice as that may be, is technically wrong because you went through too many steps. All right? So just kind of watch out for that. Not to just plug myself for you taking second semester here.